Now let us discuss existence and uniqueness of solutions of general differential equations. If you try to think a little bit about it, about how to construct differential equations, especially from vector fields, then you could probably invent Euler's method yourselves. It is a very, very natural thing to do. So basically, imagine that here is our differential equation, and we want to begin with at this point. So y of -2 is 0. It's our initial condition. So the initial point here is -2, 0. It's here. So at this point, we can calculate the direction of the motion. So the direction of the motion should be, the first entry is always 1, and the second entry would be, so here t is -2, -2 times cosine of -2 minus 0. Right? So in other words, so we need to point this vector, to draw this vector, which is -1 and -2 cosine -2, which is the same as cosine 2. Right? So we plot the vector with coordinates 1 and -2 cosine 2 here. And then in order to construct the next point, we just move along this vector. And then we repeat the procedure. So then we get to this point. Then here t is -1. Y is already, I'm not sure what it is exactly, so let's say it is 0.9 for the sake of the story, 0.9. Then we repeat the process, right? So then the vector of motion is 1, and the next part is, the next coordinate is t is -2, I is -1 already, -1 times cosine of -1 minus y, and y is, say, here it is 0.9, for example, 0.9. So which is 1, and here we get minus cosine 1.9 or something. Yeah, and again, I'm not sure what it is exactly. But the important part is that we plot this vector with coordinates 1 and minus cosine 1.9, and then we just move by kind of make one step in the direction of that vector, and then we come to the next point, and then to the and so on. So every time we plot, we construct these points step by step, and every time we move in the direction of the underlying vector calculated according to the right hand side from the direction field. So then with 4 steps we will get this broken line, but we could try to make more steps. So we could make 8 steps, and each time we increment t by 0.5. Then this broken line looks kind of smoother, and looks like it is better following the direction field. But then if we try 16 steps, then it's already very smooth. You can't really see that it is actually a broken line. But if it is 128 steps and so on, so the more steps you make, the smoother it becomes. So that's Euler's method. So Euler's method is approximating solution of a differential equation as a broken line, like in terms of these little steps. So a few points, right? So it always approximates the actual solution. So which means that if you take the limit of these piecewise linear curves, then you will get the actual trajectory, the actual solution of the differential equation. So here we did it for a single differential equation, so which means that we did it on the plane. where the one coordinate is t and the other coordinate is y, but it would work without any change if it's not a plane but rather a space, or I don't know, a high-dimensional space, so that is for systems of equations. What it kind of may go wrong here is that, so notice that here, if you compare the endpoints, I mean, the point that we reach in 4 steps, that is then 8 steps, then 16 steps, then 128 steps, and so on. So every time we increase the number of steps, so the endpoint here, it is roughly the same, so it stays around. But as we discussed already, it is possible that solutions of differential equations, they go to infinity in finite time. So it is possible that when you do these several approximations of Euler's method, then they would go like this. In the beginning, they are kind of close to each other, but then at infinity they become more and more, sorry, not at infinity, but at the terminal point they are further and further apart. So that's what might go wrong, and that's why it is actually a very tricky thing that to prove that there is always a unique solution of the differential equation and that Euler's method converges to it. It is true, but it is hard to prove. So also what I want to mention is that Euler's method is just the first simplest method to solve differential equations numerically. But the philosophy here is clear. If we cannot solve the differential equation explicitly, then what we should do, we could construct an approximation on a computer. And this is called numerical methods. And there are a lot of numerical methods to solve differential equations, and that's a really big theory. And those of you who choose to do applied mathematics, you will have numerical, the core module in numerical analysis, and you will probably learn some of these. But those of you who don't do this course, you just please know that the basic idea of these numerical methods is something like Euler's method. So all of them are just like refinements or improvements of Euler's method. If you read how it works, it's not hard to program it. So whenever, if in future you have to program a numerical method, then you'll be able to do it. But in MATLAB, Octave, or I don't know, R, I think in most Python, in most modern languages, all those libraries to solve differential equations are already pre-programmed. So when you do your project, you don't really have to program Euler's method from scratch. You will have to find out how to use the existing MATLAB functions. Although Euler's method is very simple, so maybe you prefer to program it yourselves.